Okay, so today I'm going to talk about two things. Power plants, coal-fired and nuclear, and the chemistry and all that good stuff. Also, I want to talk about half-life. Half-lives are kind of twofold in some respects. They are graphically reasonable. When I say reasonable, to understand. And then if you look at the mathematical side of it, it gets kind of tricky. So we're not going to do that. I'm going to show it to you, but you can either use that process or you can use the graphical approach. Okay, so let's talk about power plants. Okay, now the reason I'm covering power plants is energy is always an important topic in everyday life nowadays, particularly politics. And it's important to understand there are like six types of energy production modalities. Two I'm going to talk about today are coal and nuclear. But there's wind, there's solar, there's tidal, there's hydroelectric, there's a number of them. And I like all of them. Unfortunately, our government likes a few of them actually focused on one. All right, so let's talk about this now. Okay, this is a schematic of a coal-fired plant. Um, all energy production facilities take energy prime to energy double prime. And what do I mean by that? I don't mean to be real cryptic, but basically we take one type of energy, convert it to another type of more usable energy. That's the important part. More usable. That is electricity. Okay, so we have wind power, which turns the turbine with the wind. Turbine turns a generator, produces electricity. Hydroelectric. Water pushes a turbine that generates electricity. Photovoltaic is the only one that converts it directly to usable electricity or energy. And then there is coal-fired, and also under coal, we're going to put oil. It's mostly coal, and then actually natural gas. Basically, fossil fuels. Okay, but this schematic here will represent all the fossil fuels. Okay, so today we're going to talk about two main types, the most popular types of energy production in the Western world, and probably, let me make that even broader, the world. Okay, so we've got a heat source. And let's see, let's do the heat source in yellow. Okay. And the reason why I'm differentiating the heat source is because with nuclear, that's the heat source. They're the same in terms of heat sources. The heat source is used to boil water. Okay, so let's home in on that. So we've got some kind of a fossil fuel here. Illustrated with coal here, but again, it could be natural gas or oil, or I mean, we can basically it's a fossil fuel. That's burned, and it's burned to heat water. And where does the water come from? The water comes from some source. Now, the source of water comes from some reservoir or lake, river, ocean. Now, ocean is bad. Usually it's not usable because of the salt. However, it's useful in an emergency situation. Okay. So you need to know this about the heat source. This is the formula for heat source. Now, in this case, I'm using coal as an example. And there are 4 types of coal. There's anthracite, bituminous. There's a number of different types of coal. On the average, it's about this guy here, C180 H362. Very, very large molecule. Under ideal conditions, which don't exist, this is the chemistry. We've got coal, crushed to a very fine powder so that there's a high surface area. We've got oxygen, and under ideal conditions, we've got this as products. So we've got combustion reactions always have carbon dioxide and water as products. And we have lots of heat, which is interesting. And then we have one of the byproducts of using particularly coal. We also have it with oil, not so much with natural gas. Natural gas is the cleanest of the 3. But with coal, they always talk about this clean coal, which is an oxymoron. There is no clean coal because coal produces ash. And then the question is, what do you do with the ash left over? Well, customarily, what they do is they put it in a pond. It's a black water pond. Horrible for the environment. Horrible. Also, you've got burning ash, and ash is lightweight in mass, so it's easily becomes smoke. Okay, they've got something called a scrubber that pulls out the upper ash and deposits it in the disposable pond as well. Okay, so you've got these big giant ponds, and pond is kind of a misnomer. It's just a big body of water that's black, and it's horrible for wildlife. It's horrible. If you have a storm, a lot of these coal-fired plants are around in the Northeast, in the East Coast, where they have lots of northeasterners and hurricanes that spill this ash pond into nearby rivers and lakes. That's one of the big cons of coal fire. Okay, so the idea here is now you need to explain how this thing works. So we are going from fuel, which in this case is coal, we're going to burn it, and we're going to heat water to high pressure steam. And I'm going to put emphasis on high pressure steam. The steam comes from water that's usually from some kind of a reservoir. It could be a lake, could be a pond specifically designed for this, and it's turned into steam. The steam is blown into a turbine, a gas turbine. That turbine speeds quite high. It turns a generator. The generator produces electricity, and that electricity is jacked up to 50,000 volts over high tension wires and carried away. Now that water is recycled right here in the condenser. That's to recycle the water. So there's no need for a constant stream of water unless it's evaporated. Now, the problem is the water is no longer liquid, it's steam right now. So we have to condense it back to liquid water. Okay, and that's the purpose of the cooling tower. It cools the water to condense the steam into liquid water. Most modern power plants, coal or nuclear, have cooling towers. SMUD, for example, and a good friend of mine was a very high level district manager for SMUD, and his job before he retired was to dismantle the nuclear power plant there at SMUD, and it took about 5 years, took a long time, and that's one of the cons of both power plants, whether it be nuclear or coal-fired, is that the disassembly, when you're all done with it, what do you do with it? Okay, well, you've got to disassemble the cooling towers and deal with the ash pond in case of coal. Lots of disadvantages. Okay, so let's talk about, so just real quickly, let me review how this thing works. Okay, you need some kind of heat source. In the case of a coal-fired or fossil-fueled nuclear power, fossil-fuel-powered power plant, you need some source of heat. Okay, in this case, it could be coal, gas, natural gas, oil. Those are the typical sources of energy. And we heat water to high pressure steam that turns a turbine, that turns a generator, that produces electricity. The water is recycled, so you need some kind of way to cool the water back to liquid water. So this is liquid water here. And this is steam, which is gaseous water. Okay. And this is the big issue here. And this. Okay, so let's talk about pros. Okay, pros is relative inexpensive startup because there's no giant shielding needed because of the radiation and all this stuff. You just basically build a big boiler with very efficient plumbing to vent that high, extremely hot steam into the turbine, Turbine turns a generator, we produce electricity. Cooling tower, you just have initial cost of the water source, which could be an existing river, lake, or reservoir. Okay. um, Inexpensive fuel. Coal is inexpensive. It's mined in extremely large mines that are open. They're called open pit mines. They're huge, huge. And in volume, you get very inexpensive coal. Now, we export a lot of coal as well, by the way. Okay, so those are kind of pros. And also, as a pro, it's low tech. Um, Probably the biggest technology hurdle is these scrubbers up here. That's the most technology is built in there. Okay, cons. Um, um, Tons of greenhouse gases. If it's as clean as possible, the least destructive greenhouse gas is carbon dioxide. But the problem with coal is made from old plants and animals millions of years ago, and they have nitrogen and sulfur built into the proteins called amino acids. Those amino acids contain sulfur and nitrogen, lots of nitrogen. Nitrogen converts to nitrous oxides and sulfur oxides. That's like nitric oxide, hydrogen sulfide. This is called acid rain. Okay, so those are the major cons. Big time polluters, greenhouse gases. Pros, inexpensive startup, inexpensive fuel, and it's low tech. Okay, how are you guys feeling about this? Any questions about how this thing works? So you're going to be responsible for a pro and a con. You're responsible for the chemistry, and you're also responsible for kind of a general, how does this thing work? Okay. And similarly with the nuclear. Now notice the nuclear appears to be simpler. Well, yes and no. Okay, here is the chemistry. Let's go over the chemistry here. So we're starting with, this is called enriched uranium. Okay, there's two kinds of uranium, 238 uranium and 235. That is 0.5% of the total mined. So you've got to purify it. And you got to get it to, there's different grades of uranium. There's weapons grade. That's like 90%-ish. It varies a lot depending on what kind of weapon you're making. There is power plant grade, which is like 20%. And it varies a lot depending on what kind of power plant it is and blah, blah, blah. Okay. These differences are the big deal in Iran, for example, is they're claiming we're doing power plant enrichment, This is the whole concept of enrichment. And then the world sees it as weapons grade enrichments. This is like weapons grade means we're going to make a bomb. Power plant means we're just going to use it to make electricity. Now, there's some real issues with power plant grade uranium and weapons as well. You can make a weapon from power plant enriched uranium. Okay, so we're taking U-238, enriching it to make U-235, so we can then create this nuclear reaction. So we're taking U-235 and we're going to bombard it. This is the start of the reaction with one neutron. Once you get one neutron bombarded that U-235 uranium atom, it becomes U-236. Extremely unstable. That's why it immediately degrades to barium and krypton. And importantly, 3 neutrons. And gamma radiation and heat. Okay, so the nuclear reaction, in this case, it's fission because it's being broken apart. The heat source for nuclear reactors is this reaction. Now, there are like 3 or 4 other comparable reactions, but this is the most popular version of the reaction. Okay, so the uranium splits into barium and krypton. The barium is 140. This is 141, and krypton 92. Now, I want you to notice here, we have 1 times 1 is 3, plus 92, plus 141 equals 236. It's 236 because once we add the neutron to the uranium-235, we end up with 236. Okay, so lots of gamma radiation. That's one of the big problems in constructing a nuclear power plant is how do you deal with all this gamma radiation, ionizing radiation, very deadly to organisms, including humans. And then we have a whole bunch of heat. The heat is where the water is converted to steam. Okay, so you need to know that reaction along with this reaction. Okay, so let's talk about how this thing works. Okay, in yellow is the heat source. That heat source, let's go right here. Okay, so the problem with this, I guess I should back out here real quick. The problem with this reaction is it's extremely dangerous because of control. So we have 2 situations, no control, that's called a bomb. And then we have with control, that's what happens at the power plant. Okay, so how does that work? Okay, so if you look at the reaction requires a neutron to start this reaction. So that's the key on controlling this reaction is controlling the number of neutrons available. Okay. And that's where the control rods come into play. The control rods go up and down. When the control rods are lowered into the fuel rods, the reaction slows down because the control rods absorb neutrons. No neutrons, no reaction. So that's the way the power plant controls the reaction. You lower the control rods down into the fuel rods. The control rods absorb neutrons and the reaction slows down. So the real issue is, and this is a huge concrete structure to absorb the gamma radiation. So it's all done in this big dome. All reactors have domes. Underneath the domes is where the actual reactor happens. And this is more shielding as well. Okay. Lower the control rods, we absorb neutrons, the reaction slows. Raise the control rods, we don't absorb as many neutrons, and what happens is the reaction speeds up. Okay, now we have to convert the water to steam again. So we've got this reaction going, extremely hot. It's liquid sodium, about 2,000 degrees, very, very hot. And it goes and immediately vaporizes the water, that's liquid water now, to gaseous water or steam. High pressure steam turns a turbine turns a generator that creates electric power. And what we're going to do is we're going to take the steam now, and this is low pressure steam now, back to liquid water. And then that's the process. So this part is like the coal-fired plant. The heat source is different with nuclear power. And then you need to have a water source. Now, the water source is for two reasons. We need water for steam. Additionally, we need emergency cool down water if there's an emergency. So all, without exception, nuclear power plants are by a water source, either a river, lake, ocean. Now, oceans are fine in terms of number two, the emergency cool down water. Not for the water used in the condenser part. That has to be purified water. But the emergency cool down water is like period, no exceptions. You got to have cool down water. That's why frequently they're by an ocean, like Fukushima, for example, where they have that nice cold ocean water in case of an emergency. Also, these guys need electricity to run. No electricity, no pump. Boom. Bad, bad, bad. Pump there. So if the pumps aren't supplied with electricity, this fails miserably. Now that's the problem right now in Ukraine. Ukraine has the old Chernobyl power plant, and they have one even bigger than Chernobyl. And it's being compromised horrendously because the electricity is being compromised to the pumps. And that's a big deal right now, because if that thing should do a Chernobyl-like action, it would be a disaster for Europe and anything downwind. Like when Chernobyl blew up, United States received fallout, radiation fallout from that explosion. And big time Europeans received it. So to keep this thing going, you need electricity. Okay, so let's talk about pros and cons now. I need space. Okay, so pros. Endless fuel. There's a lot of uranium around, and we know how to process it from 238 to 235. And you don't have to change these for like 20 years. It's a major deal changing it, but 20 years, we've got to, with no issues with the fuel. Clean. No greenhouse gases. None, zero. Fuel is expensive, but you use it over 20 years. So fuel, in this case, the uranium-235 at 20% level enrichment, is economical, okay? Even though it's expensive to start with, it lasts for a long, long time. Okay, cons. Very expensive startup. And takedown. What do you do when you don't want the nuclear power plant anymore? You have to take it down. Very expensive. They're also expensive to build. Waste product storage. What do I mean by that? Okay, so let's look at this reaction again here. This has unused uranium-235 left over. Yeah. Because it doesn't use up all of the 235. It uses a lot of it, but not all of it. So when they change out the fuel rods still are very radioactive. So what do you do with them? They store them on site. Bad. Waste products stored on site are usually stored underwater, indefinite time. They don't know what to do with them. They do not know what to do with them. Japan recycles their waste fuel rods into newer ones, but you still have waste left over. So Japan has kind of got a handle on it better than the United States. The other problem is they're not well secured. Not well secured. That means they have one guard, if any, securing these waste fuel rods. Now, that's the problem with Fukushima, for example, is that when the tsunami hit the Fukushima plant, it dumped all this cold water into the wells and ponds that they're storing the spent fuel rods in. Just messed everything up big time. Now, because they're not well secured, spent fuel rods can be turned into a weapon. Yes. Okay. It's called a dirty bomb. Easily. It's called, you grind it up and go with a crop duster and sprinkle it wherever you want to cause intense misery. Extremely easy to make. I'm talking about any person off the street you grab can make a dirty bomb. All you need to do is a hand cranked grinder. Super low tech. No degree in nuclear physics required. We're talking about a strong arm, grind up the stuff, put it in some kind of a powder dispenser, and that's a dirty bomb. Extremely easy to make. The other thing is they also make uh, anti um, armor piercing shells for machine guns and artillery, etc. And those are used frequently whenever we have whenever we have a confrontation in the Middle East. So unfortunately for the Middle East, we have thousands upon thousands of depleted uranium shells laying around. The uh, birth statistics are awful in that area of the country. Lots of birth defects. Teratogenicity is out of line. It's totally bad. So anyway, um, the let me add one thing to the pros. Power is economical, but it has to be put in perspective of the build up costs and tear down. So it depends how you look at that. So I'm going to put that in parentheses. Okay, so that's pros and cons for each one. Um, so for the tests, you're going to need to know you need to give me a paragraph on how the thing works. The chemistry. And one pro, one con. Okay, how are you guys doing? Was that a whimper? There's a lot to this. It's very interesting, though. And you guys, very few people know how this stuff works, particularly the nuclear side. I wanted to educate you as a citizen of this country. to know how this stuff works, particularly the pros and cons. Particularly, to me, that's as an instructor, that's really important.
Can you scroll back up where the pros and cons were, like where you were making a note of them? I was just still making notes on at the
Um,
bottom.
um,
Yeah, that one. That
uh,
right there. Thank you.
Here, let me,
Thank you.
there we go. Does this make sense?
Some parts.
Yeah, and I really, I wanted to make it as basic as possible, especially when you're looking at this is what's going on in our country. You have the coal-fired stuff going on, and you've got the nuclear stuff going on. Each got their pros and cons. And it's important to understand the pros and cons when you're listening to politicians, because they don't know jack, particularly about the um, the um, the technical aspects of this. Um, they really don't. And I mentioned this in a lecture about the series Chernobyl. Highly recommended over break. Highly recommended. It's very well done. I can't recommend it highly. It's really well done. And um, and when you're looking at that series, think of 3 Mile Island, which happened in the United States. It's not as bad, but it was, a pretty bad situation also. Okay. My cough is not doing so well. So see, as soon as I as soon as I mention it, I start coughing. So excuse me. I'm going to cover equilibrium on Monday, and I'm going to also cover half-life. I was going to do that today, but I'm just going to play it easy and cover that on Monday. And that'll be it for Unit 2, is our lecture on Monday. So, you guys have any thing you want to say?
No, that's it. Thank you. Hope you feel better, Professor.
Yeah, me too. You guys have been really nice to me. I want to tell you that right up. You've been really nice to me, and I really appreciate it. Um, you've been very patient with me with this stupid cough. Um, I just want to tell you, I really appreciate it. Um, the One of the reasons I'm 76 years old, and for the last 10 years, people have been telling me, why don't you retire with a big R, Ferguson? And I keep telling people, it's just, I really enjoy working with people, students. And I like the topic, obviously, because that's what my background is. But there's also that whole social contact. I really enjoy working with students and making it a class that they feel it's have some value, not just a class as a prerequisite, but some value. For example, we talked about today. I want you to have a sense of value of why we're talking about this stuff. It means a lot. So anyway, sorry, you guys. But again, I really appreciate you guys. You're um, allied health students are my favorite group to work with. Um, I've taught the 400 401 series, and they are nice students also, but they're STEM students and some of them are very nerdy. They're not social at all. Allied health students are very social, and I'm a very social person. So for me, it's really fun working with you guys. So anyway, enough of that. All right, so I'm going to end this and post the video, and we'll be raring to go on Monday. Do spend some time reviewing this video though with the power plants because there's a lot to it. They basically work the same. Heat source heats the water to steam, turns the turbine, turns the generator, produce electricity. They're basic, exactly the same in that regard. And there's a lot of little details that are not the same, but in that regard, they're exactly the same. All right. Anyway, take care, you guys. You guys also have a happy, solid weekend. I think the weather is going to be improving nicely tomorrow. We're going to get Delta breeze coming. So, yay.
Yes.
Okay.
Thank you, Professor. Goodbye.
Bye.
Thanks, you guys. Take care.